tonight I only copied NVIDIA, Google, and Facebook. So tonight I'm going to give you a short introduction to deep learning, short history of and introduction to deep learning. It's very short. The breakthrough in 2006 has only effectively allowed 8 years for deep learning to become what it is today, and I'm going to try to outline the historical machine learning context and the past 8 years in the next hour or so. Because we're a data science group, I want to take some data to start, and so if just with a show of hands. So who here had heard of deep learning before they saw it in the announcement for this talk? And Harlan's taking the data, so wait till you see the flash. Who here had, who could actually explain what deep learning was to another data scientist? Not as many. You got that? Okay, good. So good. This talk is for not for nothing. Who here had been introduced through a course to deep learning? Who here had implemented at least one deep learning algorithm? Wow, didn't expect that. And who here started a deep learning company? Sweet. 8 years in the next hour, it means about 8 minutes per year. So even though I've tried to simplify and just give you the cliff notes tonight, I still suspect this is going to be a drink from the fire hose. If you get lost, just try and hang on to whatever I highlight in yellow and red. And if you could, please, this is a longish presentation, but I was feeling guilty about that until I saw the intro. I'm going to be liberal. So tonight I'm going to talk about 4 things. First is the historical machine learning context deep learning emerged from. Second is historical limitations of neural nets. Third is what's happened in deep learning technology since 2006, and now how deep learning is doing now. I'm going to start with this coverage in Forbes just to illustrate the business interests. Sanju also pointed this out. There is huge interest in both machine learning and data science right now by big companies, and Google's one of them. And right now, the most popular course at Stanford is Andrew Ng's machine learning course. And for all the data scientists here who haven't taken it, he's a phenomenal communicator. I highly recommend it. But what is machine learning I know that we have a diverse audience here. Machine learning is all about finding patterns in data. Mathematically, it's fitting some typically high-dimensional set of feature vectors to fitting a function to those, where the output might be, for instance, another function where you're fitting, for instance, the temperature as a function of time of day, for instance, or maybe you're finding labels where, for instance, you have a speech signal and you want to say what words were in that speech signal. And to some of you that might sound like artificial intelligence, and it is related, but it's not exactly AI. AI is a more general framework. So here in AI, we separate the world on the left from the AI agent on the right here. And the AI agent takes in information from the world through sensors and converts those to digital form. You can think of that as the unified data from Twitter, cell phone cameras, Internet of Things, etc. And you can think of that as this XY database here, where X are, those are observations of the world, and Y are things you know to be true about the world. And just think of that database as an instantiation of a buzzword, big data. And downstream analytics and actuators are things like Siri answering questions, where, for instance, the actuator for Siri would be the speaker when she responds to you if they ask a question, or the screen if the answer is on the screen. And in the case of an autonomous vehicle, for instance, it might be the steering wheel. But that's generally how the agent then interacts with the world. And so here's an instantiation of machine learning. Oh, and specifically, just think of machine learning as the brains of AI. That's how I think of it. At left here, you see the world. And the world is full of cats and not cats. And so this world is clearly YouTube. People take lots of pictures and post them with their cell phones. And a canonical machine learning question is, of all the photos out there, which are cats and which aren't cats? And so this is historically how it was always done. You'd start by getting a bunch of images. And since everyone posts lots of pictures of cats and everything else, getting an image database is cheap. That's this part. But labeling them by hand, this part, that's expensive. that's getting these Ys. That's what you know to be true about the world. And that's what's marked in red here. And not only that, if you ever want to separate other classes besides cats, you then have to repeat that labeling process for every other detector you want to train. So for instance, you're going to train for cars, trucks, people. So it's a recurring expense per detector. And that's one of the expensive parts. And on the right here, you also see the hand engineering of features in red. And that's also a time-consuming process, typically needed by a lot of experimentation by highly trained and specialized individuals like graduate students, postdocs, and professional engineers. And for instance, SIFT, the Scale Invariant Feature Transform in computer vision, that took David Lowe about 10 years of engineering to get right. But once you had those expensive labels and features, you could then just plug them into your favorite classification algorithm and then get out a cat detector. And so here you have an input image of cat, it says cat. You have a compass, it says not cat. You have a dog, it says cat. Not perfect, but that's how machine learning was always done. And that story was the same whether you were talking about speech recognition or object recognition. And so here you have on the left an audio waveform in the world, and that's someone saying some words. It's digitized by a microphone and then sampled as a digital utterance X, and every 20 millisecond frame gets labeled with a phoneme label. Phonemes are just the sounds we make that we string together into words, like I'm doing right now. And those are the Ys. So I'm going to start here with these meld frequency capsule coefficients, as these MFCCs. And over a decade of feature engineering went into developing these in the 80s and 90s. And these representations of speech are lossy, but they were a good representation, actually very hard to beat in annual speech recognition benchmarks. They basically worked well with Gaussian mixture models of hidden Markov models for speech. And they were very hard to beat, and that was true in 1995 when I wrote my undergrad thesis on speech recognition. That was true in 2000 when I wrote my PhD thesis on image analysis. And that was true as recently as 2008, but it's not true anymore, and it's not true because of DeepLearning. And here are the labels, those other expensive things. And so where do they come from? Well, there's this group called the LDC, the Linguistics Data Consortium, that in the 90s put together laboriously and through a very expensive process orthographically transcribed audio waveforms that matched up these sound waves with their phoneme labels. And that massive labeling of data produced these corpora that allowed speech recognition labs to train acoustic models, pronunciation dictionaries, language models, etc. And that's how speech recognition was done for over 20 years. And here's a similar diagram for my thesis. This is for medical image analysis. So think of it as an anatomical recognizer where you have a medical image and you want to say what's in it automatically. So at left you have a patient sampled by an MR magnet, and that gets converted into a 3D digital volume. And then you might run segmentation, boundary detection, and region classification algorithms and generate some features. And often in medical image analysis, at least when I was at GE and in grad school, these features were often tuned to specific problems, and you would re-engineer features every time you had a new problem. Everybody claimed their approach was general, but you wouldn't see that in the literature. So again, expensive feature engineering. And these labels, this is an even more painful story than the speech recognition story. And I saw with my own eyes graduate students and undergrads sitting in dark, windowless caves, developing carpal tunnel syndrome, drawing anatomical labels on 2D slices of 3D anatomy for years, literally. But again, this is the same story, expensive features and expensive labels. And this isn't just my opinion. Here's Joshua Bengio making the point that feature engineering is 90% of the effort in industrial machine learning. Here's Jeff Hinton making the same point in a distinguished lecture series talk. And here is Jan LeCun in 2012 at IPAM making the same point, that these are the expensive parts. But like I said, once you had these expensive features and labels, you could then just plug them into your favorite classification algorithm and then say, okay, well, give me a cat detector. And I haven't talked much about this yet, and so I'll go into that next. So there was a team at Cornell, led by Rich Caruana here in 2004, that set up a battle royale of different problems, different machine learning problems, across different machine learning algorithms, and they scored them with different performance metrics, things like ranking error, accuracy, and probability metrics. And the machine learning algorithms they looked into were things like boosted decision trees, random forest, naive Bayes, sport vector machines, neural nets, the things you would normally try. Notice a few things about this. Every one of these problems has on the order of tens to maybe 100 or so attributes. That's relatively a small feature vector size. And also they only use 5,000 exemplars per problem. So these are pretty tiny data sets. And also the neural nets, when they tested them, they only gave them one layer. And they used at max 128 neurons. So what did they find? So here's the leaderboard. They found that ensemble methods like boosted decision trees, random forest, and bag decision trees outperformed other methods on average across performance metrics. Here are those performance metrics. These are the threshold metrics. Here are the ranking metrics. Here are the probability metrics. And the ones in bold basically are the winners. And you see boosted decision trees winning up here, most of them, and then winning on average. But they also said, even though these might be doing well on most of the problems, they said, as the no free lunch theorem suggests, there's no universally best learning algorithm. Even the best models perform poorly on some problems, and models that have poor average performance perform well on a few problems or metrics. That said, so what do you take away from this kind of a leaderboard? Well, if you had a new machine learning problem and you didn't know what technique you should use, they're just saying do it in this order. And so that means neural nets, if they come in 10th, you're only going to try that 10th. So in 2004, they said neural nets are not the thing that you would try first. What happened between 2004 and 2008? Data sets got bigger, and the same author in the grand tradition of academic research repeated that study. And here you have the problems they looked at this time. And now note that some of these problems have more than 100,000 features per problem. And now they're using more than 10,000 training exemplars per problem. And so, though this is bigger data, this is still arguably small data as we talk about big data now. And also, they used, again, shallow neural nets. But what do they find? So down here, if you just look at this graph, this yellow box kind of shows where random forests start taking off and winning. And down here, you see feature dimensionality. And here you see basically some kind of, think of that as a normalized score across those performance metrics I just showed you a second ago. Which means basically if you have more than about 10,000 dimensions in your feature vector, use random forest. And you can see that on Kaggle. A lot of competitions on Kaggle, right near the top of the leaderboard, you need to throw random forest at it, that'll do pretty well. And also notice that boosted decision trees did do well for the smaller problems, so they didn't contradict themselves. And for some reason, neural nets did a lot better on this one. I can't really explain that. But that's all I'm going to say about the historical machine learning context that deep learning emerged from. So let me just summarize what I just told you. So traditional machine learning has typically involved a lot of hand engineering of features, which was time-consuming and expensive, and also labeling. And there's no universally best algorithm, machine learning algorithm, to solve all the many machine learning problems out there. And as of 2008, neural nets were yet another machine learning algorithm. I'll call that YAMLA. Yeah, I said it. So here's another Forbes article just to highlight again the business interest. They ask, what is deep learning? And they say, it's a powerful new way to analyze big data that allows computers to learn without being taught. And in this context, when they say learn without being taught, they mean do less of that labeling and do less of that feature engineering. To appreciate this slide, I'm just going to introduce these three. I'm going to start with two criticisms that you would often hear about neural nets when I went to grad school in the late 90s. You would hear, one, that neural nets are black boxes. You never know how they're going to do on a new problem. You just feed them a bunch of X's and Y's and hope that they did really well. And if they didn't, you never knew why, and there was also no way to kind of see what they were thinking. You couldn't generate data from them. They were just a discriminative model. Another argument you would hear was along those performance lines I just showed you with those Caruana papers, that other algorithms outperformed them. Here you see three people. This is Jeff Hinton, Jan LeCun, and Yoshua Bengio. And these three are responsible for what I would consider the seminal ideas in deep learning. These three persisted in this direction despite disinterest by many in the academic and scientific community for decades. And Yoshua Bengio was recently quoted as much, saying deep learning is really a conspiracy between Jeff Hinton, Jan LeCun, and Yoshua Bengio. And in his talks now and then, you'll hear him say how statisticians didn't believe him on certain points, or he'll mention rejected papers, or even a de facto policy of rejecting papers with neural nets in the title without review. And that's important context to understand that this road to deep learning was not an easy one, and these three, this slide is meant to credit these three, however late, with, I don't know, for their stubborn persistence in that area. And so down here I have triumvirate. I've never seen people refer to them like this before, but I will, because these three men really did govern the shape of this field in the past 20 years. Everybody needs a slide like this in their talks nowadays. You see in gold, this is neural net search volume as a function of time. You see that dropping off steadily since 2004. And here in blue, you see basically zero search volume for deep learning as of pre-2006. 2006 ends up being a very important year for deep learning. And then it started to take off here now just recently. And now faster even than machine learning. And so machine learning here, I don't know why machine learning came down from 2004 to 2009 and then went up since then, but think of that as a calibration curve for these two. Another thing I want to point out here, if you look at the top search volume, deep learning tutorial. So I know there are people out there that have questions about deep learning. This is not necessarily a tutorial, this is more history, but hopefully I'll make some pointers to the literature that will help you. Okay, so now we're going to do a little bit of neural nets 101, and I'm going to go back to that cat detector problem, which is basically a supervised learning problem. And remember, it was given X and Y. So X is a photo. This is my cat. And you're going to learn a label Y based on that photo. And the question is that photo a cat? And so here on the left, I've taken a slide from Andrew Ng's machine learning course. Again, very good course, I recommend it. And so what goes into a neural net? So at the bottom here, you have the input layer. And these blue circles are basically pixel values from this image. So think of those as the RGB values in the image. And the neural net has to compute some label estimate based on some parameters of that neural net. And think of that as some number between 0 and 1, for instance. 1 for cat, definitely, and 0 for definitely not cat. And these black arrows are directed weights. So they take input from the layer below and send it to the next layer up. And by the way, these orange layers between the input and output layers, those are hidden layers because you never really get to observe those. So basically, every neuron gets a linear combination of input from the layer below and then compute some nonlinear transformation. And typically, people would use logistic functions for that nonlinear transformation, and then you choose some parameters for that logistic function. But once you say that's what a neural net is, it's very easy to take an image, put it in, and get a label out. So we're done. The real question is, how do you set all those weights and nonlinear functions so that this thing is actually informative? And I'm going to talk about that next. So here are more slides stolen from Andrew Ng's course. At the top left here, you have the backpropagation algorithm. And that's basically a recipe for how to optimize the neural net's objective with respect to those weights and nonlinear functions. And a reasonable objective might be, for instance, to set those weights to minimize the squared training error, or training error is, for instance, the difference between the predicted labels and the training labels that are already hand-labeled. And all backpropagation is doing is just computing the gradient of an energy surface. And so down here you see some energy surfaces. So it's just finding, the direction, how you slide down a hill. So you can perturb those weights and nonlinearities to lower that energy. And basically these thetas, these are, for instance, those parameterizations of those weights and nonlinearities. And you basically adjust those with the chain rule. And if you do that, you can take tiny little steps that'll start getting more of the labels correct for any given training set. And incidentally, both Jeff Hinton and Jan LeCun helped flesh out this backpropagation algorithm in the 80s. And because these problems are large, you'll often use stochastic gradient descent to find a minimum of the objective. And like a lot of optimization techniques, it's susceptible to local minimum, meaning that if you start going in one direction, maybe if you have a poor initialization or you take step sizes that are too big, maybe you'll head into a local minimum that isn't as good as maybe another local minimum. But briefly, even though you had that issue, the pros were that you could do the supervised training with backpropagation to, it's basically a simple approach to learn a good discriminative model with 1 or 2 layers. But the cons were that it didn't give you a generative model, didn't learn this generating distribution function, P of x, had trouble with learning more than 3 layers, just more than a few layers. I shouldn't say 3. I use 3 as it's prone to overfitting and can take a very long time for large data sets. And just remember these pros and cons going to drive the technology development since 2006. And probably one of the most often cited reasons that neural nets can't generalize to deep architectures is what's called the vanishing gradient problem. And that was mentioned, he basically developed this for recurrent networks in 1991. And so if I just kind of give a little bit of the intuition behind why this is a problem, think of y as a very low information content variable. It's really, think of it just as a binary value. And from that, you're going to, with the chain rule, go back through all these weights. Now, this is just a cartoon with 6 neurons, but typically you'll have thousands or millions here. So you're going to use some very small bit of information to try and set lots of things, and that's the prescription for problems. And specifically what happens with the gradient here is as you start going backward through some of these neurons, that gradient will typically either explode or go to 0 and just stop flowing, so it won't reach the bottom. And basically the bottom is going to end up being, well, these hidden layers near the bottom are going to be in noise or something like, something that's not that informative, meaning that most of the work is going to be done up here near the top of the network. Okay, so I've outlined at least enough of neural nets to say what their problems were, and now I'm going to talk about what's happened since 2006. And like I said, 2006 was a big year for neural nets, and that's when Jeff Hinton and Ruslan Salihudinov, they published their paper on restricted Boltzmann machines. That's here in yellow. And I've divided the history of deep learning into before restricted Boltzmann machines and after restricted Boltzmann machines here, VR and AR. So what do you see in the era before restricted Boltzmann machines? Well, in mainstream machine learning, you'd see shallow nets, meaning 3 or fewer layers, colloquially, and they would be trained on CPUs. Near university, they were using these logistic nonlinearities, sigmoid functions. They were initializing their nets with random weights. They could only learn a discriminative, not a generative model for the data. And neural nets were yet another machine learning algorithm, like I showed you with those papers by Caruana doing that battle royale. There were some deep architectures, but these were generally restricted to a small interest group, and really Jan LeCun was, I think, the only one in that space making progress. So, 2006, restricted Boltzmann machines. I'm going to go into the next slide. Now you see people training deep networks, meaning 6 or more layers on big data. They're starting to train these with graphics processing units instead of CPUs, where now you have thousands of cores instead of tens. People are using autoencoders and restricted Boltzmann machines to learn generative models for the data. They're initializing their discriminative models with the generative model parameters. They're starting to use other nonlinearities now that seem to have better properties, like the rectified linear unit. They're preventing overfitting with things like dropout, and now deep nets are starting to outcompete some of the best state-of-the-art in the world at very entrenched problem domains like object recognition on the ImageNet database and speech recognition on the TIMM data set, for instance. And as of 2013, deep learning has started to move out of academia and into places like Google and Facebook. So, like I said, I'm going to drive these technology developments with these pros and cons. And so I'm going to focus on these first 2 cons and talk about that 2006 result. So the restricted Boltzmann machines weren't new per se. It was in 2006 that Jeff Hinton demonstrated their value in creating both deep and generative neural networks. And the key insight is to learn P of x, not just that conditional probability of label given x. And the way you do that is by making these connections between hidden and visible units, both bidirectional, there are no arrows on those lines, and bipartite, there are no arrows between individual hidden units or no arrows between individual visible units. And then you compute weights based on the average outer products between samples of hidden and visible units. And if you do that sampling back and forth even once, it's a form of what's called contrastive divergence. And this contrastive divergence estimate of the gradient is a reasonable approximation to the maximum likelihood estimator. And you can use that to learn a generative model for the hidden layer from the data only. And so when I say from the data only, that's only the x's. And remember, before when you wanted to do machine learning, you needed both the x's and the y's. Now all you need is those cheap x's. So you don't have to do that hand labeling. And in the same spirit, generative models called denoising autoencoders followed. And they use the same idea of building generative models of layers. I had to pick some things to talk about tonight, and I'm going to go over. But with restricted Boltzmann machines or autoencoders, you can just draw samples of the data X now. So now instead of that problem where you're given an image of a cat, and the job of the predictor is to say, is it a cat or not? Now you give it a bunch of images of cats and say, draw me a cat. Totally different problem. That's unsupervised versus supervised. Another great property of restricted Boltzmann machines is to get a better and better approximation of that generating distribution, P of X. You can now stack these models. And now every layer will improve things. And that allows you to get deep networks that don't suffer that vanishing gradient problem. Because now the gradient isn't propagated through all those layers with the chain rule. And now you're just using sampling. And you can do very few sampling iterations as well. And this greedy stacking improves a variational lower bound on the likelihood of the training data. And more importantly, it actually seems to work. So that dispenses with these first two cons, with restricted Boltzmann machines, the noise and autoencoders, etc. So what do people do about overfitting? And so to talk about why this overfitting result's important, let's first talk about how neural nets learn to overfit. Often, when training, a neural net will find a few features or a few exemplars that have a specific, set of features down here that might be connected through a few of these weights. They might be co-adapted. And what happens then is you get some kind of narrow groove through some connected weights that tend to be a feature that they overuse over and over again. And even to the exclusion of other evidence, when other evidence is available to the neural net to learn, oh, I could also use this to make that same decision. And what the dropout technique does is it randomly turns off half the neurons in the network every time. So every time it sees a new training exemplar, it's seeing a different network architecture. And you turn off, for instance, half at a time. And that forces neurons to learn a more diverse set of features to represent their prediction functions. Because it never knows if it's going to have its favorite features available to it. And that was kind of the problem before. So you're basically making the neural net guess. And so in Jeff Hinton's words, he says, the gradient descent can take a lot of time to pull apart hidden units, which are behaving in a very similar way. And this dropout procedure mixes things up more quickly. And then at test time, all you have to do is have all the weights on each neural net. And this is like adding noise to the data and bagging many different architectures during testing. So what does it look like in terms of performance? So if you do this process, it's equivalent, like I said, to adding noise and model averaging. So you'd expect that if you're adding noise, it to do worse on the training data. And that's what you see. So if you do that training without dropout, then it comes to a lower value quicker than if you trained with dropout. But also the training error is basically the practice test you've seen the answers for, and no one really cares how you do on that data. People care how you do on the test data that you haven't seen yet. And the story's opposite there. On the test data, what happens is, as a function of training epoch, the error starts coming down, reaches a minimum, and then hits into the overfitting regime, and you're overfit to the training data. That's if you don't use dropout. But if you do use dropout on that test data, it comes down to a lower value than even the minimum error if you didn't use dropout, and then stays there. It's more stable down here as well. And the same thing happens with the cross entropy here. So the argument here is that now these classifiers are generalizing better on the test data. And similar to the way dropout turns off outputs of neurons, a new technique called Drop Connect from NYU randomly turns off inputs to the neurons. And this has been shown to have maybe some better theoretical properties. It's recently outcompeted Dropout in a few benchmarks. But it's basically another model averaging technique where every training exemplar basically gets a different architecture. And so here you can see if you don't use either, you get this overfitting. And then the argument here is that the error can come down with Dropout, but it comes down faster and stays lower with Drop Connect. But in any event, this idea of mixing up the architecture during training has been shown to effectively mitigate or even eliminate overfitting across a wide range of problem domains. So that's that one. And that was that's the third major con. And there are other techniques that do that, like max out, fast dropout, and stochastic pooling. And so people would also make this argument that neural nets were slow to train. And that was true. So for really large image analysis problems, even high-performance computing clusters could take months to train deep architectures. And keep that in mind as I walk you through this next example from Google and Andrew Ng's group at Stanford. So in this work, they took 10 million frames from random YouTube videos and trained a deep, sparse autoencoder with convolutional labels. And just to remind you, autoencoders are a kind of unsupervised learning that only needs those X's. They don't need the Y's. And so here's a simplified cartoon of that autoencoder with the input layer at the left and then the encoding on the right. So the image is hierarchically encoded from left to right with more complex compositions to the right here. And maximal responses of 3 orange neurons are shown. And so here, closest to the data, you get basically this 45-degree angle edge or line response here, meaning that that's what this thing is looking for and responding to. And you typically see that with a lot of autoencoders on images. You'll see that they learn edges as kind of a low-level representation of images. And then they start composing that into more complex things. So for instance, they start composing faces. And that's what this neuron responds to maximally. And they learn there's a cat in there. And that was just trained on YouTube videos. And no one ever labeled an image as having a cat or not, or having a face or not. It just learned those. And that was the big result here. And so how well did they do on that? Well, here you can see the separation on the labeled data set between non-faces and faces, and you see they do very well with that neuron. And same thing with cats and non-cats. And so that was a huge result because they did this without labels. That said, at the time, this was also the largest known neural net ever trained. It had 1 billion parameters. And though 1 billion might sound like a lot of parameters, that's still only about 1/millionth the number of neurons in your human visual cortex. So it's still tiny compared to us. But they didn't need labels to learn those detectors. And that was such a big deal, it was covered in the New York Times. And the New York Times covered the gee whiz factor of the result, but the title also said a lot about the computational costs. They needed 16,000 cores to get that result. So that result, though groundbreaking, was impractical. You'd need $4 million of computer hardware running at 1 megawatt, and you need a huge server room to store all those machines. You couldn't replicate it as a mere mortal. You could only replicate it as Google or Amazon. So it seems that slow argument is still valid. Slow or expensive, however you want to phrase it. So the question is, how can this scale for the masses? So Adam Coates, a student in Andrew Ng's lab, he followed up with this paper on GPUs, deep learning with COTS HPC systems. And so the key result here is that you have a choice when you design your compute infrastructure. You can either scale out, that's what that original cat detector did, or you can scale up. Scaling out just means use more machines. Scale up means put more computational power in each machine. And he did that with graphics processing units. And the difference between CPUs on those scale-out machines is they might have maybe tens of processors, but GPUs can have thousands. And this team put 4 cards with 1,500 cores each in their machines for a total of more than 98,000 cores in 16 machines. And remember that original work had 16,000 cores and 1,000 machines. And then they connected their machines with InfiniBand, a very low latency communication fabric. Then they replicated that 1 billion parameter network that took 1,016 core machines to train with 3 machines. And it ran at 200 images per second and processed 14 terabytes in 3 hours. And by any definition, that is processing big data now. And this paper is just an example, just an illustration of how GPUs allow deep learning at scale. But in practice, effectively every one in the deep learning community now uses GPUs to train their deep networks. And Sirisan has a paper on the same thing. And before I go on, I just want to call out a few specs on modern GPUs. So every column here is a GPU from NVIDIA, and every row is a spec. And so first, I just want to point out that you can now get thousands of cores packed onto a modern GPU for only a few $100s. And I also point out memory bandwidth here, because often the bottleneck in some of these computations with GPUs is just getting the information from the host memory onto the core so you can do your computation, and then doing your computation and getting it back onto the host memory. And that's memory bandwidth. That's how fast you can move that. And here you have 224 gigabytes per second in one of the older cards, and now with the GTX 780 Ti, 336. That's an increase of 50% in memory bandwidth. And again, hundreds of dollars, almost 3,000 cores. Let's see. Okay, so that's where we are. So we're done with the cons. So I'm going to give a little bit more, I guess, intuition and theoretical background on deep learning before I give you where deep learning is now. Let's see. So I've talked about deep learning, but I haven't really defined depth. And if you call depth the maximum number of computations from input to output, you can start looking at depths of many kinds of different machine learning algorithms. And with this concept of depth, for neural nets, it's just the number of layers after the input layer. And using that same concept of depth, you can say, what's the depth of decision trees? Well, decision trees have effectively 2 layers of depth. And how does boosting change things? Well, boosting maybe adds 1 layer of depth to your machine learning algorithm. And bagging, I would argue, is similar, but I don't know if that actually adds 1 layer. So now, go back and think about that 2004, 2008 set of Caruana papers that said boosted decision trees and random forests win. Well, with this notion of depth, they're comparing depth 3 architectures that won to depth 1 architectures because they only gave their neural nets 1 layer. So arguably, they were really saying deep architectures won. And so don't take that argument too literally. I haven't done the rigorous experiments myself, but it's one way to reinterpret those results. Another sort of intuition behind deep architectures, it's sort of an intuitive theoretical defense, is that as you squash a deep architecture of n layers to n-1 layers, at some point going from n to n-1 layers may require exponentially more neurons to represent the same function. And that means at some point deep architectures may explode into very fat and inefficient architectures for representing the same function as an architecture with just 1 more layer, meaning that these are compact representations of those prediction functions. And this does not contradict the universal approximator theorem, which says that you can model any function with 1 layer. That theorem does not tell you how many neurons you need or how to train it. So, another intuition behind deep learning is that you sort of compose your results from sort of low-level information to more abstract information. So here you have edges, and then you have parts of letters composed from those edges, and then you have those parts of letters composed into letters. And I highly recommend, if you're interested, this talk by Ruslan Salakhudinov. He's one of the original ones on the 2006 restricted Boltzmann machine paper. He gave this intro at ISB last year in San Francisco in April. There's a lot of great material in there. But generally, internal representations capture higher order statistical structure. So these learned abstractions of objects also depend on what data we use to train them. So in this work by Hong-Lak Lee, we see the common oriented edges that I talked about at the first level. And then you see compositions of those at the next level. And this is if you train with a lot of different kinds of images. It just learns these generic kind of filters. And for anyone who doesn't know this, it's known from neuroscience that the visual cortex sees with neurons that often look a lot like these first-level filters. And remember, nothing was ever programmed into deep learning that said, learn this. They just happened to rediscover them as you gave them a lot of data. And Andrew Ng will also make this point about speech recognition. He says that the same way unsupervised feature learning discovers edge detection, unsupervised learning on audio spectra of speech discovers phonemes. And that representation of phonemes, that was that low-level representation of the MFCCs, those mel frequency capture coefficients in the speech recognition example. That's what they were trying to represent, but they did that with hand engineering back in the 80s and 90s. And now deep learning does it better than they did. And these abstractions at the second and third level depend on what the database was of images that you use to train them. So if you give them a bunch of faces, it'll learn parts of faces, and it'll learn to reconstruct whole faces. If you give them cars, it'll find parts of cars, and then whole cars. You give them pictures of elephants, find parts of elephants, and pictures of elephants. You give them chairs, it'll parts of chairs, chairs. And that's all I'm going to say about the intuition behind deep learning. Now I'm going to go into where deep learning is today. So I'm going to return to that closest thing to the cat detector that I talked about at the beginning to motivate the machine learning problem. And Kaggle recently provided 25,000 pictures of cats and dogs and asked entrants to train a classifier to discriminate between them. And all of the top 10 results of 215 entrants on that Kaggle competition came from deep learning. And the best result got 99% correct. And almost all of those entrants used features that were learned from a more general image recognition challenge called ImageNet. I'm going to talk about that a little bit, providing some empirical evidence that learned features are reusable across tasks. But in every respect now, deep learning is currently the best way to build that cat detector I talked about. And specifically, Overfeed out of NYU won, but the code is only licensed for internal research and you can't modify it, which is a non-starter for a lot of people for code bases. But there's also options like Decaf from Yanxing Jia at UC Berkeley, and that was recently replaced by Cafe, and those are both BSD licensed. And 9 out of the top 10 used either one or the other or a combination of both. Here's a student of Jeff Hinton's, George Dahl, explaining how his team won a Kaggle competition predicting molecular activity of drugs. And you can read the story, but the key messages are: 1, learn the representation. Don't use your feeble brain to try and engineer the features by hand. And 2, reuse the learned features across tasks. When you've finished learning to predict one activity, reuse those features learned when you learn to predict a different activity. Here's another deep learning win on a different Kaggle competition on predicting salaries. This is Vlad Min, a student of Hinton's, coming in first of 289 teams. This is just a laundry list of recent deep learning wins on international machine learning benchmarks, from detecting mitosis and histology images, segmenting brain tissue and EM imagery, Chinese, Arabic, and French handwriting recognition, and better than human performance on German traffic sign recognition. And all these are international competitions with open benchmarks. And the point here is that deep learning is winning a lot of these. So before that Merck competition, George Dahl, who I just mentioned, and also Abdel Rahman Mohammed of Jeff Hinton's lab, they did internships applying deep learning to speech recognition. And their experimental deep learning approach outperformed all other methods that have ever been tried for acoustic modeling on the Timmett data set. They replaced, specifically what they did was they replaced those Gaussian mixture models with discriminatively trained deep neural nets after unsupervised feature learning with stacked restricted Boltzmann machines. And just for historical perspective, prior to applying deep learning on that Timmett data set, the speech recognition community as a whole had made 1.6% progress on word error rate over a decade. Then applying deep learning reduced that error rate immediately by 1.1%. So that's multiple years of contributions by an entire community, or equivalent to. And again, these were internships. In a recent review at ICAST, deep learning has been shown to outperform all other methods in a host of different speech recognition subtasks, and I just refer you to that paper. I'm not as familiar with speech recognition literature, but this is one of those tasks. And at this point in time, to my knowledge, all the major speech recognition engines of Google, Apple, and Microsoft are all using deep learning. So I point out this example because there were about 20 people in the room in Barcelona in 2012. And the silence of who cared about this result was deafening. I think I might have been the only person at that conference who didn't actually have a paper there. So technically there was only one audience member. But I was doing work in this area, and I was interested in both brain anatomy and deep learning. And in this task, what you have to do is harder than it looks. And you have to do it very accurately for it to be useful as a connectomics result. But you have here different neurons, and they're separated by plasma membranes. And all you got to do is just say, find me the plasma membrane so I can draw a color diagram that separates all the different neurons. Looks easy, right? It's very, very hard. And here's the leaderboard, and Sirasan and Alessandro Gusti, they won by a large margin. But that's a lot of different domains for deep learning to win in so few years. And these aren't new problem domains. These are some of the most entrenched problem domains in the world. Speech recognition and object recognition have been AI bottlenecks for a long time. And I'm not making the point that those are solved by any means. But now, clearly, the best results are coming from deep learning. Okay, I'm going to spend some time developing this ImageNet result because this ImageNet breakthrough to me is sort of the standard bearer for why deep learning is such a big deal. And I'm kind of an imaging guy, or an image analysis guy anyway. And for those of you not familiar with object recognition, this result from Krasevsky, Sutskever, and Hinton's 2012 ImageNet paper, it may look mundane because I know you've seen results like this in maybe as early as the mid-'80s in such peer-reviewed literature as the Terminator movie and RoboCop. But for those of us in the lab, this was something of a holy grail, autonomously automatically annotating images with semantic labels. And in the annual ImageNet competition, you get credited for an image if the true image label appears in your first 5 guesses. And under each image, you see in gray the top 5 guesses from deep learning, and you see the true label here. So these first 6 are all credited as correct because the true label actually appears in those top 5 guesses, and these are wrong, arguably. And in the grand tradition of all computer vision results, you see here a picture of a Dalmatian. It's labeled as cherry because it was standing over a bowl of cherries, so it's clearly the wrong label. But they say, look, we got Dalmatian. And then even these things we saw, we thought they were graves, we thought they were elderberries or currants. But take that as you will. Computer vision is full of results like that, these magic examples. And in this case, they cherry-picked their example. If you haven't seen this, and not many people have, please do. I think it's some of the best 2.5 minutes on the internet. That's Alex Krasevsky giving his 2.5 minutes on the ImageNet result, where the deep learning team got 15% error, where the best computer vision labs in the world at object recognition got 26% error. That's a huge result. Here's the leaderboard. Again, deep learning at the top. So how do they do it? Because these are not computer vision people. These are deep learning people, neural net people. So they trained a huge 60 million parameter convolutional neural net on 2 GPUs. And I haven't talked about them, but convolutional neural nets are special kind of networks where individual neurons only see inputs from a local region in the layer below, not the whole layer below. So they don't have connections between distant parts of the image. And at the very top of the network, though, they did use fully connected layers and dropout. So they train on 1.2 million labeled training images, and I showed you some of the 1,000 classes in the first slide with the sample results. And the test set is an unseen set of 150,000 images. And then here on the right, I just show you that they're, again, learning the same kind of edge filters that you might find on generative models, but they're Gabor-like or color filters or texture filters. So what are some of the tricks? So data augmentation is one of the tricks, where they use both sampling and adding noise in a way that respects image state. So for sampling, they just took large patches of the input images at random offsets, and they used their left-right reflections and used all those as training images. And then at test time, they would sample every one of the 4 corners and the center and do left-right reflection with those and get their average label, and that would be how they'd incorporate it at test time. They also use PCA to smartly add noise in the RGB space, and these ended up reducing error by about 1%. But in general, they were perturbing every image in training, so they never saw the same image twice. And this data augmentation basically inflates your training data. And I like to think of it culturally, that those GPUs made training so fast, they said, oh, 1.2 million images? That's not enough for us. We'll use 90 times that amount of data. And that was culturally new, and a lot of those other algorithms couldn't even do that. So the ImageNet breakthrough also used rectified linear units. Here's the rectified linear unit nonlinearity, where the more standard was this logistic curve. And you see the training performance is a function of training epoch here, where these are the rectified linear units, and here are the logistic units. And basically, you can get the same training error in about quarter the time it would take if you used logistic neurons. So it's training faster. There are other great properties of rectifier networks, and this paper by Garat, if you're interested, is a good start there. There's also a great paper by Ian Goodfellow on MaxOut. Okay. What else did they do? They did local response normalization and overlapping max pooling instead of non-overlapping max pooling. And max pooling is pretty standard in convolutional nets, where basically you just take the local maximum from the layer below. And that improves accuracy by about 1.5%. And recently, Matt Zeiler and Rob Fergus at NYU, they also showed how a stochastic max pooling approach can help prevent overfitting in convolutional layers, the same way dropout does in fully connected layers. And I refer you to that paper if you're interested in that. And the last thing I'm going to say about the ImageNet result is just how simple it was. They used dropout, rectified linear units, and trained with GPUs. And technically, you could do almost all of that back in the 80s if you wanted to. Dropout was kind of new. But everything else was pretty straightforward. And they released their code under a BSD license. And that's all I'm going to say about those ImageNet results. And now, just for perspective, I'm going to take a look at that team that came in third. So before I get into these slides, I am a computer vision person, or I have a computer vision history. And I just want to make sure it's clear that Andrew Zisserman is one of my all-time computer vision heroes and role models. And these slides aren't meant to take anything away from the phenomenal results of the other entrants in the ImageNet result. They're really meant to give some credibility to that deep learning result. So Andrew Zisserman is the head of that lab at Oxford that came in third. And here you have his first page this is the top of his first page on Google Scholar. 13,000 sites for this book, 2,000 for the next site, 2,800. You go to the bottom of the page, still 800 sites. You can go to page 10, and there's still object recognition contributions with more than 100 sites. And for those of you who aren't familiar, that's a lot. So think of Andrew Zisserman as a standard bearer for computer vision, and Jeff Hinton's team is a standard bearer for deep learning here, and that's a field arguably outside of computer vision, muscling in on computer vision's home turf. And so Jan LeCun, he starts this Google Plus discussion. He says, the talk at ImageNet made a bit of a splash. So it doesn't take long before another computer vision expert weighs in with, I think ImageNet is just too easy because chance on ImageNet is 1 in 200. To which Jeff Hinton replied on the same thread, I predicted some computer vision people would say that the task was too easy. Then he points out Jitendra Malik and Andrew Zisserman both validating that ImageNet performance is a real benchmark. And then he concludes, trying to discredit a system that gets 84% correct by saying you get 0.5% correct by chance is a bit desperate. And that sounds fighty. And as you can see here in red, luckily we have this crowdsourcing to determine who won that debate. You see that Elisha Afros, he got +5, and Jeff Hinton, he got +22. So Jeff Hinton here, he's 4.4 times as correct as Elisha Afros. So take it another way. You read a lot of stuff on the internet, and the question is, who were these people involved in this in this thread? Do we care what they think? Are they the local idiots? And I have to be agnostic about saying whether they're local idiots or not, but they sure did have a lot of Google Scholar citations. Jan LeCun, 19,000 sites. Elisha Efros, 11,000 sites. Jitendra Malik, 77,000 sites. Jeff Hinton, 71,000 sites. And Angela Simmons, 63,000 sites. So this is not a standard chat room debate. This is an open debate between scientists heavily invested in their arguably separate communities. And Jan LeCun weighs in at the end with this statement. He says, the computer vision community has been skeptical about deep learning and feature learning, but there was the same kind of skepticism from the machine learning community until 4 or 5 years ago. Thankfully, results on standard benchmarks have a way of quieting down theological arguments. He said that at the end of 2012. The 2013 ImageNet result, every one of the top entrants used deep learning, just for historical perspective. And deep learning continued to reduce the error rate. So to put that ImageNet breakthrough in perspective, just cultural perspective from a data scientist's point of view, they outperformed the best computer vision labs in the world at a task those computer vision labs had invested decades in. And arguably more importantly, this is a real sentence from the paper. We trained the network for roughly 90 cycles through the training set, which took about 6 days on 2 NVIDIA GTX 580 3GB GPUs. And so to translate that for the data scientists in the crowd, this technology is available to everybody. Specifically, that winning result was trained in Alex Grzybski's bedroom using hardware you can acquire for less than $2,000, and the code was licensed BSD. And it's worth thinking about that for a second, just to absorb what it means to the data science community. So I'd updated the cons as I went along. I'm now going to update some of the pros. So deep architectures aren't only simple, but they're fast and cheap to learn both discriminative models as well as generative models. Results aren't just good anymore, but they're state-of-the-art on international competitions for deep architectures on some problem domains. Unsupervised feature learning is faster, less expensive, and gets better results than the alternative of hand-tuned feature engineering. There are open source, permissively licensed resources and a furiously active research community extending these code bases daily. There are solid theoretical and empirical reasons to believe deep models are efficient or compact representations of prediction functions that scale well. And you can still make that argument that, that these deep networks are slow to train. But if you make that criticism of deep learning, you also have to ask, what's the alternative? Compared to what? And that's something that is worth discussing. Just as kind of some other cultural benchmarks, MIT's Tech Review, they called deep learning one of the top 10 breakthrough technologies in 2013. So who noticed that result on ImageNet? This is Jeff Hinton, this is Ilya Sutskever, and that's Alex Grzybski. They presented that paper in the fall of 2012, and by March of 2013, Google had bought the company they all worked for. And by May, it incorporated it into Google Plus personal image search. And that is lightning fast for this kind of technology to be incorporated at that scale. So that's all I'm going to say about that. And this kind of goes along with Sanju's point about Google being foresighted here. Not to be outdone, Facebook's Mark Zuckerberg himself showed up at a machine learning conference, MIPS, just a few months ago, and he personally announced Facebook hired one of the other of the 3 deep learning triumvirate, Jan LeCun. And when Wired asked Jan LeCun what he'd be doing, he said, well, I'll be writing papers like an academic, and I'll be incorporating some of this technology into Facebook. And that's what academics do. So that kind of freedom is now available in industry. A few weeks ago, Netflix also announced an initiative in deep learning to improve personalization. And so market demand for data science, I think this crowd is probably well aware that it's, intense. And I'm just going to give 2 data points here on deep learning as a specific part of data science. So DeepMind just sold for $400 million in January of this year, and they had 75 employees. And in the same Bloomberg Businessweek story, they say, Microsoft, Facebook, and Google find themselves in a battle for deep learning talent. Last year, the cost of a top world-class deep learning expert was about the same as a top NFL quarterback prospect. So, I'm sure you guys are thinking now, wait a second, Harlan said he was going to cut down the hype. He was going to tell you what was true here. So what is the problem with hype here? And what is hype? So I've talked a lot really about the past and present of deep learning. I haven't really talked about the future. And that's what I'm going to define as hype. Promising things that deep learning has not yet done, but you say is going to do in the future. And this thermometer here, this is meant to be a metaphorical hype meter. So if you say deep learning is yet another machine learning algorithm, I'd say that is unjustified empirically with data from international benchmarks on machine learning and also on recent Kaggle competitions. Similarly, if you said there's no reason to look at any other machine learning algorithm, boom, latent Dirichlet allocation, any other because deep learning is going to solve it all. Deep learning cured cancer. That is also ridiculously hypey. But what's reasonable? I think some cautious optimism in the results we're seeing, without some reckless assertions about what's going to happen in the future. And I think that's all I'm going to say on that. So Andrew Ng also has, I highly recommend this talk as well. It's a great background on deep learning. So I'm not going to go through these point by point, but two meta points from this slide. So one is that if you're going to make a criticism of deep learning, it has to be current. And you'll hear a lot of criticisms that are just repeated because they've heard them somewhere else, but they've since been overturned. And another meta point here is that it's that compared to what argument? That if you're going to make a criticism of deep learning, you also have to level that criticism at competing technologies, and that's where I think the good discussion happens. All right, we've come to the conclusion, and this is the Return of the King style conclusion, where there's like 5 different endings that each take. I'm going to go through 3 different versions here, and I'm going to summarize first with text. That's this slide for the people who like to read. I know there are librarians in the audience, and this is for you. And then I'm going to give you a picture, and then I'm going to give you just kind of like the whole talk in 2 bullet points. So, I'm not aware of every deep learning result out there, and it changes daily. So this is just my understanding of the facts. Deep learning allows you to learn multiple reusable hierarchical abstractions of features from the data itself. Deep learning provides breakthrough or state-of-the-art performance across many mature problem domains as becoming a practical machine learning resource through a number of recent developments, including data availability, algorithms, culture, and hardware. In terms of data, huge standardized data sets, some labeled, are available to learn from and benchmark on. Algorithmically, improvements include convolutional neural nets, dropout, rectified linear units, max pooling, restricted Boltzmann machines, autoencoders, data augmentation, and curriculum learning. Culturally, many open source permissively licensed code bases are available, including PyLearn 2, CUDA ConvNets, Piano, and Torch. In terms of hardware, GPUs now allow scale up to big data with a modest investment of resources. Deep learning is disrupting established machine learning technologies like continuous speech recognition. Deep learning mitigates the expensive hand labeling of objects and hand engineering of features. Deep architectures can learn to draw samples of data from unlabeled corpora. Deep learning can scale to terabytes and exabytes of data, that is big data. Deep learning has a huge learning capacity that resists overfitting with dropout, drop connect, stochastic pooling, and max. This is the picture. So this is what the past looks like. This is a line, think of that as 2006. And in the past, you would start with a modest data set, typically smaller, and you'd have some labels, and you would train a shallow network, maybe 1 or 2 layers, using neurons with this kind of nonlinearity, this logistic function. And you would get out a supervised classifier, this conditional probability of the label given the observation X. And it would be okay, it would be good. It would be yet another machine learning algorithm. And you would typically write that in C or MATLAB, and you'd run it on your CPUs. And you'd use backpropagation, and you'd typically engineer those features by hand. And every now and then, 2004, 2008, you'd have these kind of academic evaluations, presumably by a disinterested academic that would dispassionately have just as much expertise in one algorithm as another, and you would just trust that the results they were getting you could then extend to your problem domain. So now, what are people doing? Well, they're using much bigger data sets, all 4 V's of big data. They're training deep architectures. They're creating generative models of the data here. They're getting away with using fewer labels by leveraging that generative model to generate their conditional probability of a label given the observations X, and often that's state-of-the-art performance. And inside these networks, they're now using other nonlinearities like rectified linear units and max out. They're still using techniques like backpropagation, but now they're incorporating things like dropout, stochastic gradient descent, asynchronous stochastic gradient descent, autoencoders, wake-sleep algorithm, curriculum learning, etc. A lot of other stuff that I didn't have time to talk about. And now they're leveraging GPUs built on a substrate of other technology, like CUDA, Torch, CUDA-Mat, Piano, PyLearn 2. And now that you'll typically use, GPUs, but you might even use a cluster of GPUs. And if you want to see how your particular algorithm is performing on a particular problem, you can now just go to Kaggle. So now you don't have to hope that there's some, I don't know, dispassionate academic that's going to solve that problem for you. Now there's self-interested parties that are all trying to get their algorithm to the top of this leaderboard. And that's a way to deal with that no free lunch theorem. So it's not a free lunch because Kaggle costs something to run, but it's a cheap lunch with Kaggle. So now, this is just 2 bullet points for the slide. Remember the machine learning history that I kind of started from. People would hand engineer features, and now you say we can solve that with deep learning without labeled data. And remember, labeled data was that other expensive thing that you needed to generate those features. And now those features are arguably reusable, which makes these things generalize better. That's that P of X model. Not only that, now if you want to generate a state-of-the-art discriminative classifier here, generating that conditional probability for the data, you now might need a lot less labeled data to do this, because you can now initialize with the parameter from this generative model that only used unlabeled data, and now get a really good classifier here. And I highly recommend this talk. This is Jeff Vinton's Distinguished Lecture Series talk. I think it was May this past year. Yeah, May. I'm not going to talk about the future of deep learning. Yashua Bengio has a paper where he makes some guesses as to where deep learning is going. So I highly recommend this paper if you're interested in that, what's next in deep learning. He also, Yashua Bengio, did an Ask Me Anything on Reddit, and that was a phenomenal resource for really thoughtful answers to a lot of deep learning questions, both from neophytes as well as really involved investigators. So that's all I'm going to say about that. And this is just the singular value decomposition of the future of deep learning, given that it's coming from Bengio. I didn't mean to include, I don't know, even in the title, conditional probabilities. So I did have to omit quite a bit in covering deep learning. So what are some of the key things? There's a lot more I omitted, but so one thing I didn't talk about is this dark art of training. It's right now just a small club of people who know how to get these things to work well. So even though you might see them at the top of the leaderboard, you might not be able to do that yourself without a lot of trying. There's some tricks, and they're covered in a few papers, but in general, I think this is still poorly documented in the literature. Also, I didn't talk about sparsing. Sparsing is very important for some of these deep networks. The way I told the story, just to come clean, you don't really need that unsupervised pre-training anymore. If you have enough labeled data, you can just kind of dispense with it. But it's just a better way to tell the story, because remember, restricted Wilson machines are a central part of that story. I like to put that in there. So that's really just a style thing. You don't want me talking about recurrent networks. I don't understand. But there's some great results in recurrent networks, and I highly recommend this recent paper on Word2Vec. I think it was Thomas Mikolov. And here are the resources. And I think I'm ready for questions.
Right now we have time for questions. If you need to go, that's okay. But we do have time for questions, and then we will move to the bar.
So it does make it a little easier if you come out or just raise your hand nice and high if you have a question. So
Test. How can you compare and contrast this stuff with some of the more advanced unsupervised learning techniques? I'm thinking, for example, like PCAs with kernels, independent component analysis, even PCA itself, SKU as well.
So, I mean, let's backpedal from kernel PCA just to straight PCA and why certain other dimensionality reduction techniques don't do a good job because they're constraining the parameter space in a way that's just not natural and not really expressive like these deep architectures are. I would start from that argument of depth, where there's a recent paper by Joshua Bengio on how many different partitions you can generate from these different types of neurons. And I would just argue that if you had a deep enough architecture, you could use ICA, you could use kernel PCA as layers of the architecture, but the argument is that as you compose them, you would have a much more efficient representation of them. So it's basically more expressive. Now, that's not to say that that gives you an automatic training algorithm, because what I've talked about here, restricted Boltzmann machines, you know, let's just say you use contrastive divergence to train those. And apologies to the rest of the audience that never looked at neural net. But if you use contrastive divergence, you have an algorithm that lets you set that network parameterization, and you can train the deep one. So I would argue that we have ready approaches. If you tried to swap in ICA or kernel PCA, you might not be using backpropagation, for instance, if that answers your question. Okay, I've been asked to go back to the resources slide.
The slides will be posted later, by the way.
I just want to know if you have any idea of room for quantum computers with respect to deep learning. So
there is a really great talk by the guy, I forget his name, he's the head of D-Wave, and he talks a lot about, actually if you went to, where is it, this, and you went to the jobs posting just a few months ago, you would have seen only 2 jobs posted. One was my former job, and the other one was a position announcement for D-Wave, which is doing quantum computing, and I don't know a lot about quantum computing, but I know that there is at least one kind of, saw a YouTube interview with the head of D-Wave, very smart guy, but he thinks that there's a lot of potential there, because arguably the way GPUs unlock potential here, that's in kind of like a von Neumann architecture, but deep learning just unlocks so much more computational, but potentially, I mean, depending on the number of qubits, but you know, he was talking hundreds, and I don't know, they're actually creating those machines now. But that's too esoteric a connection for me to make right now. I'm only familiar with what's being done in the literature.
Could you say just a little bit more about where a deep learning network with minimal supervision learns what a cat is? Where does it get the information?
Sure. I'm going to try and answer that. It gets it from all the data. And so there were just, oh, that's a lot of slides. Sorry. I'm getting there. Okay, so this was, again, unlabeled. All that data coming in. There were 10 million frames of YouTube videos coming in. And the way I think of it is they were repeated enough in the data here to become modes of that distribution, right? I mean, there are going to be some peaks that are repeated enough. They say, well, this is important enough to represent in that low-dimensional space, and as you go from here over to here, it's becoming a lower-dimensional space, and so they're important enough to encode. Other things that don't happen that often, they think, well, it's not that important to encode. And you saw that with the, I'm gonna regret this, aren't I? You saw that here too. So here, these were unlabeled, right? And it's learning faces, basically because these are modes of that distribution, modes in that high dimensional space, not a peak of a 1D function, you know. We can finish it after. I mean, if anybody else has a good idea, go ahead.
It's all in the data, Doug.
What's that?
You're only looking at cat photos.
No. All right, so in this one, all you're looking at are photos of faces, and it learns a model for faces. In this one, you're learning models of cars, because you're only showing it pictures of cars. In that original, the Google Cat Detector, they gave it all different kinds of images. That was 10 million random YouTube frames. So that had cats, that had faces, and it had a bunch of other things. Like there was another detector that I didn't talk about, but it was basically a human profile, not profile, but basically a head and shoulders detector that basically responds only to head and shoulders because a person is a very common object. It's a mode in that distribution of images. If that is answering, yes? Oh, okay, good, great.
I had just picking up, you started the talk by saying that it was very expensive to do feature extraction and labeling. And so picking up on the same topic, you kind of left the training a little bit open-ended. I wonder if you can just make the connection stronger between, you know, if in the past we had to do a lot of feature extraction by hand and labeling by hand. Can you just kind of close the loop for how training's done in the deep learning world relative to how much labeling goes into it, how much feature extraction goes into the data?
Okay. So like I said at all right, do I complicate this by saying that I'm about to lie to you? No. So I'm going to tell you kind of a fib that kind of fits with the story that I told, and then I'll tell you that you don't even need that. How does deep learning find these features, these things? And those features were like those neuron responses, those maximal neuron responses I was just showing you. It learns, oh, that's an important thing for me to represent, just like features were an important thing to represent. And the way deep learning is going to do it is it's going to look at the data and do this sort of Gibbs sampling and generate hidden layers that can reproduce the input distribution. So if you're doing that, that means it's a good representation of all those images. Those are the features that you wanted, because they're the things that basically separate different kinds of images. And that's what they find with discriminative training. So then what they'll typically do is they'll initialize their big network. So that here they're stacking those restricted bolts machines, and then you can initialize a big neural net with the weights you learn from this unsupervised pre-training. Remember, no labels were needed there. And then with that network, you then give it some labels and you do some fine-tuning on the discriminative classifier, and now that basically mitigates your need to rely on labels. That said, as basically ImageNet results point out, they didn't do any pre-training, meaning you could just dispense with that and it'll learn some features just with enough label data. Is that?
That's helpful. Yeah.
Okay.
Still some dark art.
What would be the? Yeah, but that's not supposed to be the dark art. Dark art's supposed to be other stuff, but.
What kind of process is used to decide which nodes to knock out?
Oh, it's just purely random. All right, so just to restate the question, what process is used to decide which nodes to knock out? And I think he's talking about this. You randomly turn off nodes. Just random, uniform, half of them. No, I'm not gonna say the more detailed version. You don't really do it on convolutional layers. You do it on fully connected layers, but just modulate that little detail.
Let's take two more quick questions.
I just had one here. You talked a lot about how well deep learning does at image problems, and I'm wondering if that's a necessary condition, or what about image problems make deep learning such a good tool for that? And when you're applying it to other problems, do you need to translate those problems into like an image so that it's easier to solve?
I would say what you really need to do is translate your problem into a feature vector. Because when I showed you how deep learning was doing empirically, it didn't depend on it being images. This is an image one. This is not. This is not. Some of these are. Actually, wait, are all those? I guess those all are. Here's speech, not images. Don't overread my emphasis on images because that's my background. That's just what I'm most familiar with. And it's just easiest to show you a picture of how it's doing with images. It's harder for me to kind of go through the deep learning to do with acoustic models and say, here, see phonemes. It just doesn't, I don't bracket like I do this.
Quick question over here. I'm sorry.
Hi. My question actually follows pretty nicely on the heels of that one. So you touched very briefly on recurrent neural networks, and yes, you said.
I also said don't ask me.
Yeah. Well, I already had the question in mind.
I guess we can go back.
It wasn't going to be too deep a question. It was just so it was thinking back to that slide about shouldn't get the hype factor too strong and all that. I mean, I do feel like some of the things that recurrent neural networks are able to do, you're doing something almost more akin to structure learning than you are just here's a set of homogeneous features. You can do things like segmentation and sentence parsing and semantic some certain types of semantic analysis, and of just if you have any intuition at all about where that might be able to take you.
So you started off with a question about recurrent neural networks, and then it led somewhere where I'm not sure I follow what I'm answering.
So you said that you'd only be able to answer questions about recurrent neural networks on a more superficial level. So I asked a superficial question, which was basically what do you think that they'll show themselves to be capable of in the next few years?
What did I say about hype? I said I'm not going to hype. So I'm not going to talk about what they can do. So why don't I talk about what they can do?
Okay.
So recurrent neural networks. So all I talked about tonight were feed-forward neural networks with a limited depth. So this one has, for instance, a depth of 1, 2, 3, 4, 5, 6, 7, 8. So about nine layers. And then the autoencoder also had about 9 layers. What happens in a recurrent neural net is it goes to this layer and then back, this layer and back, and there can be loops. And what that's like having many, many more layers. So now go back to that argument I made from the point of view of depth, that as you squash an n layer architecture to n-1 layers, that it can become a vastly inefficient network for representing the same function. So now, if you say that depth is important to compactly represent functions and have them scale well, I only talked about limited depth, finite depth architectures. Recurrent nets are arguably infinite depth. So are they going to be infinitely compact? I think there's plenty of evidence from, I'm not going to talk out of school, no, all I'm going to say is there's reason to believe that they have more depth to better represent certain functions. Is that enough?
Yeah, sure.
All right, and I would point people at that Mikolov paper. That's just I think phenomenal work.
Next year you can tell us the answer.
Yeah. You stand up here.
There's also a full paper out there of parsing sentences to figure out like what words are good and bad based on Rotten Tomatoes. Recurrent neural tensors.
It is now after 9. We should probably
I think he's going to go with it.
Call it here, but
a better cat detector? John, what were you thinking? Stealth is the key to the cat-dog balance. Because of your talk, now every Tom, Harry and Fido know how to find us. Look at me. I am wearing a pair of bunny ears, and why? Because of you and deep learning. Thanks. Thanks a lot. Way to pack them in. Way to work a room. Way to make my life harder than it needs to be. So much for the free lunch theorem.